Okay, welcome to Chapter 11. We are almost at the end of our new material, and this chapter is concerned with hypothesis tests for means. So it's going to be very similar to what we did in Chapter 9, a hypothesis test for proportions. And a hypothesis test is done when you have a commonly assumed or value or status quo, and you suspect that that is not correct. And so you're going to run a test to see if the evidence suggests that the commonly assumed value is not correct. So it's different than a confidence interval because in that you don't know what the commonly assumed value is and you're trying to estimate it. So we're going to start off and see how much sleep AP Stat students get on average. You're supposed to get 8 hours of sleep per night. I don't think you do. So again, the commonly held value is that you get 8 hours of sleep. So I sampled 10 students in a previous year, and this was the value of how much sleep they get on average a night. We want to first calculate the mean and standard deviation of my sample. So put it into the calculator through Stat Edit, and then go to Stat Calc, one variable stats to get the values. X bar, so the statistic from my sample is 6.15 hours, and the standard deviation from the sample is 1.19. Now, if I'm running a hypothesis test, I need to define my parameter. So mu, because I'm dealing with means, represents the true mean hours of sleep for Mrs. Bolger's AP Stat students. I also have to define my null and alternative hypothesis. My null hypothesis is what's commonly held true or assumed, and that is that you get 8 hours of sleep. So mu equals 8 is my null hypothesis. The alternative hypothesis is mu is less than 8 because I believe you get less than 8 hours of sleep. Next, when we're doing a hypothesis test, is we have to check conditions. Same three conditions. Random, we were told that I did a random sample of 10 students. 10%, we would be checking to see is 10 less than 1/10 of all of my AP Stat students. Well, no, it's not this year. So we would have to still proceed, but in my conclusion, I'm going to have to mention this. We have to check to see if it's normal. Well, the ways we check for normal is the population normal? We don't know that. Is the sample size greater than or equal to 30? Again, no, we don't know that. So we make a dot plot. And looking at my dot plot of the hours of sleep, there doesn't appear to be any strong skew or outliers. So I'm going to assume it's normal, or approximately normal. Next, we need to give the formula to find the mean and standard deviation of the distribution of X bar and calculate the values. So the mean of my sampling distribution is the same as the mean, the null value, which is 8. The standard deviation of my sampling distribution is found by the standard deviation of the population divided by the square root of n. Well, remember, we don't know what the standard deviation of the population is, so that's why I use the standard deviation from my sample to estimate it. It's not perfect, but it's going to give me an estimate. So the standard deviation of my sample divided by the square root of the sample size. So 1.19 divided by the square root of 10, and I get that my standard error is 6.376. So that is my standard error and my mean for my sampling distribution. Next, we want to draw a picture and calculate the test statistic. So the picture looks like this. My center is 8, and the value I'm looking for is 6.15, because that was from my sample. What was the mean of the sample? So I'm trying to calculate this area right here. I cannot use a normal distribution, so I can't use the mean and standard deviation. I have to use a t distribution and tell what the degree of freedom is. My degree of freedom is going to be 9. The test statistic, it's no longer a z, it's going to be t. Okay, so it's t. And the way we find it is our statistic minus the parameter divided by the standard error. So 6.15 is the mean of my sample minus my null value, because that is what my parameter is, divided by the standard error, which I just calculated. Okay, and that gives me negative 4.92. And did you catch I misread my own writing? That should be 0.376 up here. So that is my standard error, which is what I divide by. So again, it's the statistic minus the parameter divided by standard error. And my formula for that is x bar minus mu divided by s sub x, the standard deviation from the sample, divided by the square root of the sample size. And that is called your t-test statistic. And it's going to operate very similar to a z-score. Okay, since we are working with means, the t-statistic is a t-value, and we're going to use table B to find the p-value. So the way we do this is get out our p-table. We've got out my table, and again, I'm looking for this t-value of negative 4.92, and we're going to look at it as a positive value. So when I'm looking on here, I've got to look for my degree of freedom of 9, and I'm just looking for the closest value here to 4.92. Well, it looks like over here is the closest value. That gives me a rough estimate of my probability of 0.0005. It is a very rough estimate. Instead, we're going to use the calculator to get a much better estimate. So to get the value from the calculator, you're going to go to second bars, choose option number 6, TCDF, and we have to enter our lower value, upper value, degree of freedom, and then it'll calculate for us. So in this case, my lower value is a large negative number. Upper value was my t-statistic. So negative 4.92, my degree of freedom was 9. And when we calculate, we get 4.1 times 10 to the negative 4. So I've got to move the decimal over 4 places. So note here, the p-value from the table was approximately 0.0005. From the calculator, I've got p-value of 0.0004. This is a much more exact one, so we will tend to use the calculator versus making a guess and an estimate. And then what conclusion can we draw? Well, because 0.0004, my p-value, is less than 0.05, my alpha, we reject the null, and we do have convincing evidence that my AP Stat students have a mean hour of sleep less than 8. We have to use caution as we did not meet the 10% condition. So that's the only thing we have to do because we didn't meet one of the conditions is in the conclusion, just state that. Okay, let's go on to the second part of this, where we're going to do a second test and do the whole 4-step process. Okay, so this hypothesis test is we're going to check to see if our normal body temperature really is 98.6. That's our commonly held value, and we're going to see if it's true. Unfortunately, we don't have time to go through and measure everyone's body temperature, so I'm using results from a previous year. Okay? And based on, again, this was from 2 years ago, the mean from my 32 students, their mean temperature was 98.237. The standard deviation of my sample was 0.822 and a sample size of 32. And we want to see, does the data provide convincing evidence that the mean normal body temperature is different than the doctor's claim? We're assuming all conditions are met. Okay, so in our 4-step process, I have my state section. I've got to state the parameter. Mu represents the true mean body temperature for all high school students. My statistic was the mean from the sample. My hypothesis, the null hypothesis, is the commonly held value. Mu equals 98.6. I'm checking just to see if it's not equal to that. So I don't care if it's greater than or less than. I just want to see, is it not equal? And my alpha level or significance level is 0.05. Okay, let's go into the plan state. First thing we've got to do is name our procedure. It's a 1-sample t-test. Again, because we're testing now, we're not making a confidence interval. T-test for mu. The do part, I'm not checking conditions because, again, it says assume they've been met. Do, the general formula is that the standardized test statistic equals the statistic minus parameter divided by the standard error of the parameter. And again, this is on your formula chart on the front page. Standardized test statistic is your statistic minus the parameter divided by standard error of your statistic. The specific formula is not on your formula chart. So because we're dealing with means, my specific value is a t, my statistic is x bar, the parameter is mu, and the standard error is defined as the standard deviation of the sample divided by the square root of n. Okay, we're going to do our work here. So we put in our sample statistic minus the parameter, standard deviation of the sample divided by the square root of the sample size. And we get negative 0.250. That is my t value, my t statistic, or test statistic. And you do need to note that down. We now need to find our p-value. So we've got to be a little bit careful here. If I look at a normal distribution, 98.6 is here in the center, and I'm looking to see if my test statistic, 98.237, so this area over here, what's that probability? But remember, I don't care if it's less than or greater than. I just care if it's not equal to 98.6. So this is what's called a two-sided test. I'm checking both sides. So the difference from 98.6 to 98.237, I have to add that to 98.6, and I get 98.963. So I need this area plus this area. That's the probability, or the p-value. If I'm doing it as a t distribution, it's t with a degree of freedom of 31, which if I'm looking at a t distribution, the center is 0. My t-value is negative 2.50. So I've got to take the p-value I get here from the calculator and double it. So I include this value. So when I plug this into TCDF, I get 0.009. But again, because my alternative hypothesis is that it's just not equal, I have to take that and double it. So I get a p-value of 0.018. And now I need to make a conclusion. So assuming the null is true, which the null was 98, is that mu equals 98.6, there's a 0.018 probability of getting a statistic of 98.237 or lower, or 98.963 or higher, purely by chance. And again, I have to have both of these because it's a two-sided test. So that's how we interpret the p-value. We then have to make a conclusion. Because 0.018 is less than 0.05, the alpha value, we reject the null. We do have convincing evidence that the mean body temperature is different than the doctor's claim. So again, remember, if your p-value is less than alpha, you reject the null, and you have convincing evidence for the alternative hypothesis. If the p-value is greater than your alpha level, or your significance level, you would fail to reject the null, and you do not have convincing evidence for the alternative. And so if we repeated this, so another class, and that class had 30 students, had a mean of 97.9 and a standard deviation of 1.6, and we want to use the t-test on the calculator to find the p-value. And when you plug that in, you get 0.023. So would we still reject the null at a significance level of 0.1? Yes, because 0.023 is less than 0.1. Would we reject it if we changed our significance level to 0.05? Yes, that's still less than that. So yes, we would still reject the null, and we have evidence for the alternative. What about if we raised lowered our significance level to 0.01? Well, at that point, the p-value is greater, so we would not be rejecting the null. And what we want to take a look at and see, how does this relate to a confidence interval? So if we were to create a t-interval on the calculator with the following confidence intervals, so 90%, 95, and 99, here are the different confidence intervals we get. 97.4 to 98.396, 97.303 to 98.497, and 97.4 0.095 to 98.705. Okay, so we've got these three different confidence intervals. Now we're just going to see, would we still reject the null with these confidence intervals? So the null value is 98.6. It is not in this confidence interval. It's not between these two values. So we would still have to reject it. Because remember, the confidence interval is all the plausible values. If I were to do a confidence interval at 95%, the confidence interval is a little bit wider now, but my null value of 98.6 still is not between these two values. So again, I would have to reject the null. And finally, if I look at a 99% confidence level, it's gotten even wider. Excuse me. And now the value of 98.6 does fall between these two values. So it's within the confidence interval, so I would not reject the null value. So I just want you to see that you can use a confidence interval very similar to how you did significance test. And what we should be noticing between these two values is that our alpha level is equal to 1 minus your confidence level. So the alpha level is 1 minus this. And what you should notice is the decision whether or not to reject the null is the same when you're using a confidence interval or a two-sided significance test. This is not true if it was a one-sided test. So again, it's important that you remember, if this was a one-sided significance test, which means my alternate hypothesis was mu is less than 98.6, or if it had been mu is greater than 98.6, this would not hold true. Okay? So if it is a two-sided test, so your alternative hypothesis is simply not equal to, then we have this, you get the same decision using a confidence interval or the significance test. Okay, let's look at the summary of our notes for today. And again, these are all filled in. You might want to pause this as you need to. So to do a significance test or hypothesis test for means, we still have to meet the three conditions: random, 10%, and is it normal? So is my sample, either I'm told the population was normal, if that's not given, is my sample size greater than or equal to 30, and then we have the central limit theorem, or if neither of those two is true, we make a dot plot and we want it to show no strong skew or outliers. The test statistic itself is found by the statistic, which is x bar, minus the parameter, which is mu, divided by the standard error from my sample. So the standard deviation from the sample divided by the square root of n. And if I have to sketch it, a t distribution, I have to state that it's t and the degree of freedom, and then I would just mark it on my little chart and shade it. To get the p-value, you can use the table B, but I recommend you use second vars, option 6, which is T CDF. So make sure it's the T, and it's a C there, not a P. And you would have to note down what values you used for all three of these things. What was your lower T value, upper T value, and your degree of freedom. And again, remember, the lower and upper are the lower bound of your shading and the upper bound of your shading. To do the four-step process, we still have the exact same four sections: state, plan, do, and conclude. In the state section, you have to define your parameter, note down what your hypotheses are, both the null and the alternative. The null hypothesis is always going to be mu is equal to some value, the commonly held value. The alternative hypothesis is going to be that it's going to be different than mu, either less than, greater than, or not equal. Note your statistic that you got from your sample and your significance level. In the plan step, you need to name the procedure, so one sample t-test for mu. Check all the conditions, all three listed above. The do step, the general formula, the specific formula, do the work, note what your test statistic was, and the p-value that you got. Again, if you use the calculator to find p-value, you need to list all three inputs. In the conclude step, you interpret the p-value, and you make a decision based on is the p-value greater than or less than the alpha level. Once you make that decision about the null, you also then have to make a conclusion about the alternative. So either you do have convincing evidence for the alternative hypothesis or you do not have evidence for the hypothesis. And the final thing, when we want to relate confidence intervals to two-sided tests, if the null value is in your confidence interval, then the null value is plausible because it's within the interval, and if it's plausible, you would fail to reject the null. If the null value is not in your confidence interval, then the null value is not plausible, thus you would have to reject the null. And again, this is true for two-sided tests. A confidence interval will make the same decision as a two-sided significance test when alpha is equal to 1 minus the confidence level. Okay, the homework is online, section 9.1, and I will see you in class next period.